Good afternoon. Hello, everyone. Let's get up here and start. We have such a great panel today. I just can't wait to get out of their way and let them start. Let me welcome you to the second of 4 installments in this fall's special edition mini-series of WARF Essential Topics, commemorating WARF's 90th anniversary. I'm Michael Falk, WARF's Managing Director, WARF's General Counsel. WARF was established in 1925 to patent and license inventions arising from research at UW-Madison. Today we're going to have the first, or the second in a series of panels that we've been offering. It all starts with research, of course. In case you missed it, we held a session exploring the rationale for basic research earlier this month. You can find that video and this session also on the WARF website. And we have 2 remaining sessions. Research leads to discovery and often invention by campus faculty and students. And that is when they pull WARF in to help in determining if what they have developed is patentable or otherwise protectable and of commercial interest. How all that happens is the subject of today's session. And then we've got 2 more sessions coming along that will deal with commercialization, and that is going to be a great session next week with Kevin Conroy moderating from Exact Sciences. And then we're also going to have a session on investment, which completes the cycle, and that's going to be on November 18th. So we really encourage you to take advantage of all the sessions, and if you can't make it to one of them, please feel free to catch it online. I'm going to break right there and ask Kevin to come up. Kevin is WARF's historian, but more importantly, a doctoral student here at UW. And he's going to just give a little background and history on WARF, which is kind of puts it in context.
Thanks, Michael. So as Michael just told you, we're doing 4 talks about each of these cycles, parts of the cycle. Last week we did research. And as I explained last week, when looking at WARF's original statement of purpose, I discovered that the cycle is right there in the mission. This is the original 1925 document. I went back and got the browned paper because, as I said last week, you hear these jokes 4 times if you come to all of them. But as I said, as historians, we don't believe anything really matters unless the paper's gotten brown. But this is actually a photo of the original Articles of Organization that created WARF back in 1925. And if you'll notice, I read this whole thing last time, but I could hear the audience falling asleep, so I won't do that this time. But this is the one we talked about last week. And you can see right there, research, to promote, encourage, and aid scientific investigation and research. Today, we're talking about to provide or assist in providing the means and machinery by which their scientific discoveries, there's a word, inventions and processes may be developed. Next week, we'll talk about commercialization, and after that, investments, which is here as provide funds. So there's the 4 different parts of the cycle of innovation right there in 1925. This is basically what WARF is governed by today. It's been adjusted a few times to keep up with the changes in regulations and also to add the Mortgage Institute for Research, not just the University of Wisconsin. But other than that, this is basically pretty much what WARF is governed by today, the mission statement. So today we're going to focus in on this sentence, discoveries. But what constitutes a discovery exactly? How do you recognize one? And how do they matter? This is the trick. Last week we talked about research is sometimes not as easy as you think, that maybe basic research, when you think you're talking about fundamentals, might actually be more applied, or applied research you might discover something. So what does it mean to make that discovery? So I thought I'd use an example from my own research. This is a letter I came across doing some research on WARF. Picked up this letter by Edmund Fitzgerald. I was born in Missouri, but I grew up in Texas, kind of far from the Great Lakes. I recognized this name, but I didn't exactly know what it meant. And then I mentioned to my friends who grew up in Milwaukee around the Great Lakes, and they said, Edmund Fitzgerald, you mean like the boat? And like the song? And apparently I thought this might be kind of a big deal. So let me explain to you why this matters to WARF. This is Charles Slichter. He was one of the founders of WARF. He was the graduate dean back in 1925. His son was Donald Slichter, who was a WARF trustee from 1946 to 1978 and the president of WARF from 1960 to 1964. Donald Slichter also worked through most of his life at Northwestern Mutual Life Insurance. He became the president of Northwestern Mutual Life in 1958, and he took over for Edmund Fitzgerald. So it was Donald Slichter who was in charge of the decision when Northwestern Mutual Life decided they wanted to build a boat that would transport taconite ore around the Great Lakes. He was the one who presided at the meeting to name that boat the Edmund Fitzgerald. So, long story short, When I talked to my friend who lived in Milwaukee, I asked, do you think people will get this joke? And he said, the people who need to know will get the joke. But of course, when we talk about scientific discovery, we're looking for something more than just a historian's joke at a presentation. We want to find out what makes a scientific discovery important. And as this showed, I didn't know that researching WARF, I was going to have a connection to Gordon Lightfoot. You never really know where it's going to come across, but then how do you know when that discovery matters? And I think what's interesting, so in technology transfer, which is what WARF does, they have something that's called the home run. You might have thousands of patents, but only a few of those are going to be what are called home run inventions, in which they make money or they have a significant scientific achievement. One of the things that makes WARF different is how many home runs it's had over the years. One of the things that makes it unique is that it had 2 huge home runs actually before the end of World War II. So these are the 2 big ones that you've probably heard about. Harry Steinbach and Carl Paul Link. Harry Steinbach discovered vitamin D irradiation, which is most commonly used today in vitamin D milk. It made about $14 million, or about $219 million if you adjusted for inflation. The numbers in parentheses are the adjusted for inflation numbers. But it also, more importantly, helped eliminate rickets as a public scourge, right? So there's 2 different ways that you can think about this. One is that it earned a lot of money for future research, but it also accomplished a huge important advance in public health. The same thing with warfarin, which earned about $17 million, a little less than that, less than the Steinbach when you adjust for inflation. But it was the world's most widely sold rat poison, and is also, if you listen to pharmaceutical companies, you may hear this newest blood thinner is better than warfarin. So 50 years from now, people are still trying to convince you that something is better than warfarin. That's how much of a good blood thinner it was. But as there's not a coincidence that next 2 names you're going to see, these are the 2 big ones that have happened since 1968. Professor DeLuca, who's right here, and Professor DeLuca, I apologize if these numbers are a little out of date. It's kind of hard to keep up sometimes. But here are the numbers: 591 million, 755 million. But again, more importantly, treatments for osteoporosis, for endocrine diseases. The list goes on. Multiple exemplar, different drugs, things like that. And of course, Professor Sohi and his invention with parallel computing. And if you've been paying attention to the news, pending appeal, this number may actually be quite a bit bigger, and contributed to faster and smaller processors. So these are WARF's sort of big 4. But then here's another, and you'll have another one of our distinguished panelists here. Chancellor Wiley, you'll see his name there for computer chip performance. These are the other things that WARF has done that have earned over $10 million. But again, this list of human contributions is just as important. So the question is, how do you know in these things, just like me sitting in an archive picking up a letter from Invention Fitzgerald, how did these scientists know that what they had was going to lead to this? When do you know that that's going to happen? And how do you, what makes a discovery, does it have to make $10 million, or does it have to do something important? And I think all told, I tend to agree. This is Evan Ava Evans, who was a federal circuit judge on the 7th Circuit back in the 40s, and I found a quote where he said, "I cannot help but feel that every discovery is beneficial to mankind." So those are the questions we'll be talking about today in this presentation. What makes a discovery? What makes it important? And how do you know the discovery is going to contribute to mankind? So with that, I'll turn it over to the rest of our panel.
Excellent. Thanks, Kevin. Thanks very much. Before I introduce John Wiley as our moderator, let me first mention a couple things, just housekeeping. The session's recorded, as I told you before, so you can look online afterwards. That means when you ask questions of the panel, if you could use the microphone, that would be great, so people can pick up your questions. And then use your name tags afterwards. We're going to have dinner or drinks. We hope to do it around 5. Hopefully we can sort of stay on track and then have a chance to mingle with each other and with our panelists. So if I can bring up John Wiley, I would introduce him. I feel silly introducing him. If you don't know John Wiley on this campus, student, the chancellor, held most jobs in between, and a great inventor of ours. And so I'm going to turn it over to you, John. And
well, first of all, it's an honor to be asked to host this panel, or to moderate it. In this group, I'm not an inventor by any means. I've got a total of 7 patents to my name, 3 of them at Bell Telephone Labs, and 4 here with WARF. I was going to tell you a little bit about the one that they asked me to speak about, but I'm not going to do that. I'm going to save some time and tell you that my very best patent of all time, WARF refused to file for a patent. Really pissed me off. The mantra of an inventor is find a need and fill it. Well, my daughter had 2 cats. What do you think my need was? The litter box. nastiest place in the house. So I invented a power-ventilated cat litter box. I constructed one, I tested it worked like a charm, and I wanted WARF to patent it because is there a need? If you have a cat, you know. They didn't do it. That was their biggest mistake of all time. Because the need is still out there. Well, compared to Hector, who has more than 1,500 patents, if you count the foreign counterpart patents, my 7 is not even a blip on the radar screen. So what I'm going to do is just turn it over to the panelists, let them tell you about how they got their ideas, what their inventions were, and then we'll take maybe 10 minutes each, something like that, and try to end by 5. It's a little bit of time at the end for question and answers, okay? So we'll go alphabetically, starting with Hector.
Well, John, I'd like to say a couple of remarks before I talk about some of the things that we were able to do. That is, I just want to point out that the importance of WARF, not that you don't know the importance, but the University of Wisconsin ranks among the most sterling universities in the world as a research institution. And I got to say that WARF is in no small measure responsible for that. WARF was 25 years ahead of any other institution to create a way that inventions could support further research. And one of the most important things that it did do is that inventions have to be protected not simply to make money, but one of the chief things that drove Harry Steinbach, I was Steinbach's last student, so I became very good friends with him and learned a little bit about how he thought. The real reason he originally patented the irradiation process was not to make a pile of money. It was to protect or to keep people from using the claims of that irradiation for non-beneficial uses. For example, he told me that there were 7 cars of irradiated beer sitting on the rails in Milwaukee ready to be shipped before he got a court order stopping it. Irradiated beer was being sold as a way to fortify your bones. So one of the chief reasons that he decided that patenting was important is to keep it for the good of the population, in addition to, if it were successful and did yield funds, that funds would be funneled back to support further research. So I just thought that insight in Harry Steinbach, and he was terribly innovative. I think he really conceived WARF. He got Don Slichter to help him organize it, but it was his concept. He tried originally to give the first $1 million, which was deposited in the bank by Quaker Oats, to the university, and the university administration thought about it, but they did not want to be connected to commercial money, and they took the position, which is still unique among all universities, that inventions belong to the inventor, not to the institution. There isn't another institution that takes that position. And Steinbach, having this invention, having the money in the bank, which he refused to touch, still wanted to be sure that it got back to help further research across the campus. And that's when he and Dean Slichter got together and came up with the concept of WARF, which is just an incredible organization. And it's morphed to meet the needs of the campus. I mean, when we needed buildings, we got buildings. When we needed research support, we got research support. And I think it's evolved into an outstanding organization, and it was from the beginning, and I think Wisconsin should be very proud of it. So getting back to, I was very fortunate because I was Harry Steinbach's last student, inherited his lab, and he sent me away to England to learn about tissue cultures, thinking that I would do something very different. But I got stuck on vitamin D and really began to learn how it worked, and isolated and identified the active forms of vitamin D, and it became apparent that many of the resistant bone diseases that were untreatable before could now be treated. And so this began my career in in the area of synthesis, isolation, and identification of biologically potent compounds. And I've been lucky that WARF has saw fit to file these patents, and some of them have been successful. And I'm just glad to be here to tell you about such a great organization. John, I think that's all I want to say to start with.
Thanks, John. So let me just say that Hector, it's a great pleasure to follow you, because one of the things that I learned about when I first started learning about the interface of chemistry and biology, which is really where my work lies, I learned about the concept of prodrugs, compounds that aren't quite active on their own, but need to be metabolized to make an active entity. And really, Hector is the pioneer of that whole area. So one of the things that Hector was saying, and I think something that really WARF has embraced, is that cycle between very basic conceptual discovery and then protecting those discoveries that might have commercial benefits. So I think that studying the active components really taught us about a way of making drugs that we really didn't know about prior to Hector's work. So, so that's just an example of that interplay between basic research and practical benefits. So my own research has focused on the biological roles of carbohydrates, and we really have always been very interested in basic concepts. How do these cell surface molecules function? They really work as kind of cellular ID codes. And so there's a lot of basic science to do, but then WARF has allowed us to take advantage of some of the practical outcomes. So one thing that may not be clear to people who do basic science or who think about science is if you don't protect your discoveries, often you can't translate them. So if you find a great precursor drug and it's not patented, even if you don't want to develop that drug, it's never going to be looked at by anybody if it's not protected. So especially for pharmaceutical industry, for you to translate any basic discovery into potential benefits to people, you need to protect that technology. Otherwise, others won't look at it at all, and it won't be developed. So that's another issue with regard to the benefits of WARF, because they provide protection and help for basic science to actually translate fundamental findings into useful products. I don't know that I need to say more, so I'm going to pass it to Dan.
Well, sitting up here with these three, I'm a third-year assistant professor, so I've got my work cut out for me. But my name's Dan, and I'm an assistant professor in electrical engineering. And some of the work that I work on is in electrical and electromechanical power conversion. So that's the types of systems you would see that, you know, drive an electric car, or wind turbines, our utility system. That's where I live and play. So for me, I've always kind of worn the hat or mindset of, you know, how do I solve a problem? It's always, I've never been per se motivated by direct discovery, so I guess in that sense I'm not a very good scientist. But for me personally, I always look and say, okay, something's been done a certain way for many, many years. How could I completely change it for the better? Is it possible? And so I just sort of start out along that way, and that actually started for me back when I was a graduate student here. And so I think it's worthwhile to point out a little bit of my story in that regard, because without WARF, none of it would have ever happened. And so when I was a grad student, I was working on my PhD in what's called power electronics. So the magical black box that turns electricity from one form to another. And during that time, I set up, for my own purposes, outside of my lab work, a lab at home, because what's more fun than doing lab work at home when you could, and instead of doing it at school? I could do both. My fiance and then wife hated it, but it was great. So, for me, I was doing research and I started inventing things. Namely, I wanted to redefine how the electric motor is made. So rather than relying on copper and steel and these rare earth elements that are semi-precious metals and also have various environmental impacts and sustainability issues, I wanted to completely change how we do that. So I just started doing it in my spare bedroom with friends. And so parallel to that, and I started publishing in peer-reviewed journals, without an advisor or anything. I just said, I can do this on my own. And then along the way, I said, wait a second. If I want to translate this to anywhere, how do I do that? And it struck me as, okay, I could be a grad student in a bedroom that submits a patent someplace that I can't afford to hire an attorney to write it, so I'd have to do it myself. And I am an atrocious lawyer. So what's my option? And also, if I did have the patent, what good is it? A patent's only as good as your ability to enforce it. It's not like I could take on GE or Ford or anyone like that. So what do I do? And so I was very, very lucky and thankful that I had WARF at UW-Madison. So what else could I have done? And so very much serendipitously, I had the opportunity to take my intellectual property to WARF, and then WARF reviewed it, and they wound up filing, I think we're up to the 5 patents on it now. But now I've got a startup company, and the technology's been really well received in my academic space, and so which has led to me getting lots of government funding and peer-reviewed journal articles, all that great stuff. And I got hired back as an assistant professor here, which is somewhat outside the norm because most of the time we don't, hire our own. But I was thankful enough that wound up happening for me. And so that journey was enabled by WARF, and also I now have the opportunity to continue taking my discoveries and protecting them and launching them down whatever path may be. So I'll turn it over to Gary.
Thank you. I've been a faculty member here for 30 years now. And what we did, I think, probably could not have been done anywhere else other than Wisconsin and the department that I'm in. What we were interested in is, trying to postulate how computers may be built 15, 20 years into the future. Only a place like Wisconsin gave us sort of the freedom and the flexibility to do forward-looking research without immediate returns in some sense. And so what we did is we postulated some models, and we identified, we had to try and simulate those models. So we built computer simulation models. The one other thing that really permitted us to do what we did was one of my colleagues, Maron Livney, was building the system called Condor that allowed you to do lots and lots, that took cycles from machines that weren't being used, like in student labs at night or people's on desktops at night, and allowed us to do literally tens of thousands of simulations without having to buy the computers ourselves, which we didn't have the resources for. And so we identified a problem, saw a problem, but didn't know how to solve it. And it took us lots of efforts over the years to postulate a solution, have the high of, oh, I finally figured out how to solve the problem. And then as you try it out, you start going down and say, oh, this is not going to work. And then you try and get off that low again with another potential solution. That doesn't work until finally we came up with it. So you go through the classical research cycle of multiple highs and lows until we finally came up with something that worked. And when we did, actually, a few years before that, I didn't know what a patent was, to be honest. And one of my graduate students taught me what a patent was. He was from Baraboo. And so he and I filed our first patent, and this was the second patent that we filed. He taught a lot of the other students what a patent was, and then we learned more about it. And we decided to, this was something that likely is going to be very important in the future, and we approached WARF, and we filed a patent on it. And eventually we were right, we saw 10 years later, people started using this, and it became key technology. One thing I do want to mention, especially for the students in this room, is when you see some success, you think that, oh, those people were confident all along. They had a great degree of self-confidence. Actually, nothing could be further from the truth. Academia is used to sort of anointing certain stars. This is the top student, you get this fellowship. This is the top faculty member, you get this honor, and so on and so on. This motley crew that I had, my three co-inventors, were sort of at the opposite end of the spectrum. Andreas Mashovas, who is the lead inventor, we turned him down. He did not get admitted. And I had to go fight with the department to let him in. And they finally let him in, but they said, no, we are not going to give him any support. So I had to somehow scrounge up with support for him to get myself. The other two, Vijay and Scott, they also were turned down by all the other faculty members before they ended up working with me. So I don't think they're sorry now that they did that. But so it's, people who come to school at Wisconsin, they're all very good. And it's just that sometimes, different people's talents get nurtured in different ways. And so it's not only the anointed stars that are capable of doing stuff.
Well, they were very efficient with their time. So I'm going to reclaim a little bit of mine and give you a couple of summary remarks and observations. First of all, thanks to the panel, they were all very gracious in acknowledging WARF and its important role in the university. All of us do. It's a remarkable institution, and it's done great things for Wisconsin. Hector made a comment about, you might have a model in your mind that patents go like this. You do some basic research with no particular goal in mind. You come across an idea, there's an aha moment, and you think this might have some use. You file for and get a patent, and then you trot it out to the likely customers and license it, and the money rolls in. Well, you didn't hear a single example of that here on this stage, and I couldn't give you one either. The patents that I got were for something called amorphous metal diffusion barriers. Common parlance. If you want to know what a diffusion barrier is, it's the saran wrap on your sandwich. It keeps the inside in and the outside out, and that's its job in life. Well, in making integrated circuits, there's a need for a layer of metal to form the wires that connect the devices on the integrated circuit. And for many, many years, up until the late 70s, aluminum was always used as the metallization. Got a lot of good reasons for that, which I won't go into, but eventually the wires got so small and so thin that they were failing because the electron current density was so great it was pushing the aluminum atoms down the wire and breaking the wire. So they had to switch to a better conductor. They either had to use thicker wires, which would reduce the ability to shrink the devices, or else they had to find a different metal. Now, the best conductor of all is silver. That's not good for a lot of reasons, which I won't go into. Second best is copper. Copper is like cyanide to the human body. Copper in silicon is disastrous. So you have to keep the copper way away from the silicon in order for it to work. Gold is the next best, and then aluminum. And so there was a lot of incentive to find a way to use copper. That was the incentive for us to develop a diffusion barrier that would keep the aluminum, or the copper, separate from the silicon. And John Parapetsko and I, John was a colleague in what was then called the Department of Metallurgical Engineering. He and I came up with this idea over a cup of coffee at the Union South and decided if we could just make thin layers of amorphous metal, amorphous meaning it's not crystallized, and it's very hard to do with metals. If we could do that, it would be the ideal, the perfect diffusion barrier. And we've managed to find a way to do it. We built it, we tested it, it worked, and we tried to license it. Every electronics company you've ever heard of was offered a license to amorphous metal diffusion barriers. Everyone turned us down. So John and I just gave up and went away and did other things. And within 2 years of the expiration of our patents, we discovered that the industry was now using copper. We said, how can they be using copper without our diffusion barriers? So we complained to WARF that we thought we were being infringed. They hired a forensic law firm to go out and buy chips on the market, take them to a lab, test them, find out if they're using amorphous metal diffusion barriers, and sure enough, they were. So we sued every one of them, worldwide. Trust me, every company you've ever heard of was infringing our patents. We sued them all, we won every case, and WARF made a lot of money. So it's not a linear process at all. And the aha moment is sometimes there, but it's not always easy to identify. In every case you heard about today, someone saw a problem that needed fixing and thought they saw a way to fix it, or spent some time working on finding a way to fix it. That's sort of the inventor's mindset. And I wish more faculty on campus who are engaged in research would adopt that, at least occasionally, because I know there are a lot of good ideas out there that could be patented and licensed or otherwise turned into commercial products or processes that would greatly enhance WARF's portfolio. I think I'll open it now for, let me say one more thing before I open it up for questioning. There are personalities in different industry groups. The pharmaceutical industry, believe it or not, is actually pretty good about coming to universities and licensing prodrugs or concepts that could be turned into drugs relatively easily. That saves them a lot of money in R&D. When I first graduated from here in '68, every major corporation in the country had a large research lab, including a basic research arm. They were all doing basic research, trying to push back the frontiers in their areas of interest. I happened to go to work at Bell Telephone Labs when I graduated. They had a huge laboratory, probably the most famous one in the country. Over 2,000 scientists and engineers. Over the years, the timescale for important progress in companies shortened and shortened and shortened. The timescale for change got shorter and shorter to where the investors, the stockholders, the managers thought basic research is not a payoff for us. Not in the next year, maybe not for 10 years. We don't know what, if any, payoff there will ever be. So they stopped funding basic research. Almost everything you have, including your iPhone, your computers, all that was born initially in industrial research labs. Today, all research that isn't directly product-oriented is done in universities. It's a sea change that hasn't been much remarked on and much noticed. But all of the important basic research in the country is being done by universities and by people like those on the stage who have done this, who have taken the inventor's mindset and made sure that what was discovered in their laboratories got out into useful, practical application. The electronics industry, at the other extreme, is a bunch of pirates. They readily, freely, easily, openly, knowingly steal from each other and from universities. So to get any penny out of them, you have to sue them. And we've got an example at the front of the table. Gary-Sohi's patents with WARF are being infringed by Apple. They've won their first case. It's now probably going to be appealed, but I have no doubt whatsoever he will prevail, and WARF will get a big payment from Apple. In my case, it was Intel and IBM and Motorola and a few others. But you really have to fight to get them to pay attention or to acknowledge your contribution to their products. Our amorphous metal diffusion barriers are used, in fact, in this iPhone, in every computer processor that you buy today, in almost every memory chip or integrated circuit anywhere, because they all use copper metallization now, and they all have to protect the silicon from it. Okay, that's more than I wanted to say about my own patents. Aside from the cat litter box, that was my best, but it never got patented. Does anyone have any questions for the panel? Yes, you need a microphone.
Many of your university colleagues in the arts and humanities and music claim that those specialties help to stimulate the creative juices. And I'm wondering if you have any ways to respond, to riff off of what I just said. Maybe in your own labs you play music. Are there any stimulants to the imagination that perhaps are well linked to other specialties in this university?
Well, I'll start by saying absolutely yes. The medical school students are so musical, there are so many of them, that they can field 3 full orchestras. Whenever I go to the Chazen, I see some of our premier scientists walking around looking at the exhibits, and I'm always wondering what they're thinking when they look at that particular piece of art. It's probably stimulating an idea that they're going to use in their research or in their lab. Same with music. All the concerts are well attended by our scientists. More so than our humanists. Anyone else?
Go ahead.
I can just say that working with artists to depict science actually often helps you think about the science you're doing in fundamental new ways. So lots of times we need to illustrate complex concepts. And so working with artists has actually helped me often see my science, because they'll ask you questions about, well, is this what you mean? And then you realize that you either don't know what you really mean, or that you don't, the way that you're thinking about it is actually flawed, the way you're presenting it. So I find that actually a really important connection for me.
I would piggyback on that, and 2 points. For me, connecting with artists and musicians, things like that, allows me to get a better handle on the rest of society. I mean, a group of scientists and engineers in a room, that's a bubble. And the vast majority of us are not scientists and engineers in this world. And so I think the arts are a common link between everybody, more so than science and tech. And for me anyway, being able to use those to connect with others, talk about my work, share commonalities is a big deal. The second point I would make is that for me, I don't get inspired by staring at my laptop screen. I get inspired when I go for a walk outside, or look at some art, or listen to a symphony, or go see a rock concert, things like that. I mean, my best ideas, and when I'm sort of in the zone, come to me not when I'm writing a grant proposal or something along those lines. And so the arts are critical.
So Joanne, I don't know if this is a direct influence or not, but I've been married for 30 years to somebody who was a registrar at a Madison Museum of Contemporary Art. So there probably has been some influence.
Well, I can only add that one of the things that music or art does is it settles my mind down, so you put everything else out of it, and it allows you to come at it in a fresh way. And music has always done that for me. So to that extent, I think it contributed to any inventions that I made.
The five of you have collectively mentored a lot of young scientists, postdocs, graduate students, and undergraduates. And I'm wondering if over the years you've seen a difference in the interest of students to work in translating their discoveries to commercialization. And another two parts to that, what encourages them, what motivates them to do so, and what holds them back if they're not inclined to go in that direction?
Well, I'll say when I first came here, that question wouldn't even have been asked. The concept of commercialization or startup was almost at cross purposes with the then academic mindset of the campus. In fact, people who got involved in commercial things, one of you mentioned this actually, I think it was Dan, were looked down on. You're not a real scientist if you're dirtying your hands with commercial or product applications. That's no longer true. Entrepreneurism is booming on campus, just booming. We have whole dormitory floors of nothing else but students who have self-identified as freshmen, that what they're here for is to prepare themselves to start their own companies. That was unheard of 30 years ago.
I want to emphasize Harry Steinbach. He tried to give dirty commercial money to the university to support research. It was turned down. And that goes to show you how the evolution took place to a point where as we developed, yes, you could do research and so forth and so on, but you had to justify your outside activities, and being commercially involved was actually held against you. And we were limited to hours that you could do this. That changed drastically, as John pointed out, where now this is actively encouraged. This is an important role of the university, to help develop industry, to help commercialize, to help our state and our nation build its economy. So that's been a tremendous evolution. I've seen it happen over the course of my lifetime.
I guess I'll just follow up to say that that also we have many more international students. And one of the things that I neglected to mention is that some of the patents WARF holds for things from my lab they're not going to make a lot of money because they're aimed at, for example, potential agents that block Mycobacterium tuberculosis. That isn't a huge problem in the developed world, but it's a huge problem in the developing world. And so the great thing about WARF is they're interested in protecting that intellectual property because no one will turn that into a drug if they can't at least recoup part of their costs. And so that's why I mentioned some of the things that I did. But many of our international students are also interested in working on things that will help their countries as well. And so that also is translatable, though not necessarily lucrative in the same way. So I think that's an important distinction also between what a university would protect and what WARF protects versus what you might find in industry per se.
If I might, I'd like to get a little bit aside because I think this is an important place to tell this audience. A major hero at WARF was Howard Bremmer. I don't know how many of you have heard of Howard Bremmer, but following Sputnik and the introduction of massive federal funding of research came with it ownership of all discoveries and patents became property of the government if you had any money in your laboratory. WARF had a moratorium on filing patents from 1958 until 1969, and Howard Bremmer was patent counsel at WARF and made friends at the NIH and in Congress to develop institutional patent agreements that would allow institutions to hold patents. And that reawakened the ability of universities to patent their discoveries and actually lead to commercialization. I can't tell you how important that really was. And Howard, I think, was an unsung hero, not only of WARF, but of the university and of the state.
The implementation of that was the so-called Bayh-Dole Act in 1981.
Bayh-Dole Act.
And Howard was a consultant and one of the authors of the bill. It conferred on the inventor, or actually on the institution. So in our case, it would be Wisconsin, or Wisconsin's representative, which is WARF, ownership of their patent for a fixed period of time, which currently is around 20 years.
One of the discoveries in McCardle Labs by Charlie Heidelberger, 5-fluorouracil, which was a major anti-cancer agent at that time, he could not get that freed up for filing, and as a result, it was developed in other countries because he published the work, but nobody really benefited from 5-fluorouracil, which was a terrible crime, really. Not just benefit, but I think it prevented its getting out among the public and to be widely used.
So computer sciences is a very recent department compared to the others. And so most of the faculty have always tried to do work that has a practical impact. And that has been actually looked down upon by several of the pure scientists. I remember my first year as assistant professor, when I applied to the research committee for funding, the interviewer at that time told me he didn't think much of our department because it didn't have much mathematical foundations. So we have, doing practical work was never looked down upon our department. It was actually encouraged and rewarded. And regarding the how many students want to go and try and do commercialized stuff, a lot of our students are foreign students, and they do not have the visa paperwork to be able to do startup companies. They cannot do it. So,
someone over here has been waiting for a long time.
Okay. I noticed Dan articulated quite nicely kind of his approach of looking at something that's been done a long time the same way, and if there's a novel way to do it differently and improve on it. I'm curious if the others have kind of their rule or their approach on how they're looking for these innovations.
Well, sure. I mean, there have always been diffusion barriers in integrated circuits. It's just that most of them were what we call polycrystalline. Means the material was partially crystallized, and in between the crystallites, there are boundaries. And those boundaries are like superhighways for atoms to diffuse along. That was the advance in making the diffusion barriers be amorphous instead of polycrystalline. And we believe that we can prove that amorphous diffusion barriers are the theoretically perfect diffusion barriers that will never be exceeded. By the way, let me emphasize something Hector said about ownership. The Bayh-Dole Act was revolutionary for universities, not just Wisconsin, all universities. The institution itself takes ownership. They can do what they want with it. They can cede it back to the inventor, or they can license it. Most universities aren't in that business and don't want to do anything about it. We happen to have WARF. We're very fortunate. So we had a ready-made way to give ownership of the patents to WARF, and WARF could then deal with them. I told you I worked at Bell Labs when I first graduated. Industry does things very differently, and if there are any industrial decision makers here, pay attention to this. Intellectual property is very important for industry. It's very important that the intellectual property be protected. Patents are a pain in the butt to get. It takes a lot of work. The inventor has to spend a lot of time with lawyers explaining the idea and modifying the language in the patent disclosure and so on. There's no big incentive to do that. In industry, the company that pays your salary and gives you your lab space claims ownership of any idea you have that you conceive of during the course of your work there. That removes all incentive to do patenting. I got several patents at Bell Labs because I just wanted to do it, and they encouraged me to do it, and I cooperated with it, but I never made 1 penny out of any of them, and I'm not sure I would do it again if I were back there. I think if companies give up the claim to own the intellectual property of their employees, they would be dramatically better off.
I was going to follow up with that. So when I was an intern as a graduate student at a company, they encouraged the interns to submit ideas for patent. And if you did well, and if it was liked, you could get like a gift card. and so I just this was a major energy company, and I just said to myself, "Is this what industry is? Like, there's no way in hell if I'm getting a PhD, I'm gonna go and work in industry if I'm just gonna get a gift card for my intellectual property." And yeah, and so it was that was a defining moment for me where I realized that I did not. If I was to stay at this is a very well-known place that everyone knows of. But if I was to stay at a place like that my crown jewels of my life would not belong to me. And that was a fundamental thing that drove me away from industry.
One of the things that I'd like to point out is often industry will offer research money, but in exchange you have to agree to give them all intellectual property. I've never accepted anything like that, and to me, the industry that does that is making a big mistake, because if they had given the first right of refusal, and so they have to pay a 5% royalty to WARF. That's pretty cheap for the kind of investigation they get at universities. And so I think there's still that attempt by industry to come in and have you do research, but they own the intellectual property. My statement to all scientists on the campus: don't do it, because you can get them to agree to first right of refusal.
I was going to say, WARF is really good at preventing us from making bad decisions like that.
But sometimes WARF isn't asked.
No, that's right. But they're really good at saying, this is not in your best interest to do it this way. Yeah. I was just going to come back to the question, which was, how do people come up with ideas, or how did the rest of us think about that? And I guess I think that thinking about the boundaries between what we know and what we don't know is a really good way to think, like, well, for me, it helps to first define what's there and then think, well, what would I like to be able to do? And that seems like what you said about the multi-parallel computers.
Yes.
Yeah.
Flexibility and freedom to do what you want.
And so for me, it was really, we've been thinking a lot about the differences in what like microbes use on their cells versus what we use on our cells. And if you want new anti-infectives that work via completely new mechanisms, that is a really productive way to think. And so I can't point to one thing, because we have a series of patents in that area, all with slightly different ideas about that, but based around a particular concept like that. So
we need a mic over here. We've got about 5 more minutes, so there's time for 1 or 2 questions more. Alan's going to take one.
So yeah.
Well, you just mentioned how do you get ideas, and I met recently Fred Stonehouse, who's in the art department, and he's a neo-surrealist. He doesn't use models. He bases all his art, he's getting to be pretty well known, on his dreams. And I must say, a neo-surrealist, he has some pretty weird dreams. But I also hear that, dreaming may help you straighten out your thinking. And I'm just wondering to what dreaming or sleeping has actually helped you. Can you think of examples? I remember one, I came up with an explanation. I was dozing. It wasn't dreaming, but I was dozing. And what happened was simply, I was in the real world for a while thinking about all the possible explanations, and then I dozed and something else came up.
Anyone?
I have a kid under 1 year old, so I don't dream much. But before that, no. For me, it was more daydreaming. Like, I could go and my perfect afternoon is to just go sit in my backyard under a tree and during the fall with a beverage and just like stare out into space and ponder things. That sounds like a vacation and a half right now. And that's where I also do most of my good ideas come from. Where, like, when I'm mowing the lawn, I'll just go into autopilot and hope there's nothing, in front of the lawnmower I shouldn't run over. But I sort of go into a daydream once in a while. That's enjoyable.
I have a lot of good ideas in boring seminars.
Alan, there are major advocates of the importance of altered states of consciousness.
I hope you didn't come to any of my seminars.
I have a question related to the collaborative process for creativity. When we try to work across disciplines, we get people in the same room and have awkward beginnings of conversations. How do you really get to something in your collaborative processes? Do you have any process tips for those of us who are striving to do the kinds of things that you've done?
This whole building was designed as an example of that. We tried to do things that would encourage multidisciplinary collaboration and cross-fertilization of different fields. And so far, it's been a phenomenal success. I won't tell you all the things we did, but if you want to ask me later, I'll tell you some of them.
So I have always been a lone wolf, not collaborated with anybody but my students. So I cannot answer that one. So.
For me, what happens to me is when I usually run into a barrier. So I'll be working on solving a problem, and then I'll get to a point where I'll say, oh, if I could just do this, but in order to do this, I would need a new material, or I would need to solve some optimization problem, or there's something that's outside the realm of my expertise, but I sort of say, oh, if I could only have this, and then I reach out to a colleague and sort of explain, this is my problem, can you or someone help me with this? And then they say, of course. But and then you just get to know that person. And I mean, for me, collaboration is, don't just go to someone trying to extract something that you need from them, but also recognize it as, this is a space that you don't know much about, and you can learn from that person, and then they can learn from you at the same time. So try to make it as mutually beneficial to each other as possible.
So there's an article that I really like called Antidisciplinary Science, and it's by this person, Sean Eddy, who basically says we need interdisciplinary people. And so I think that the interdisciplinary people are the people that can kind of bridge the gaps. So I'm really a fan of trying to mentor students to pursue interests in multiple fields. And then they have a language. So they can collaborate because they already speak, at least to some extent, maybe not as fluently, but as an expert. And then you can put together people. But it was interesting what both of you said, because Dan is still intellectually driving the research. He seeks collaborators when they'll help carry the research in the right direction. And that, I think, is a good model. It's really hard to sometimes you run into people that have different research interests and you can just start up an incredible collaboration. But that's been less frequent in my experience. The good collaborations are where both people kind of have an interest in the project but are brought together because of a common interest in making progress in a direction.
Okay, folks, we've kind of timed out. If there are any more questions, you can look us up in the reception and ask them personally. But thank you very much for attending. Thanks to the panel for their stellar contributions. And hand it back to Michael.